All right, today we're going over test corrections for Chapter 6 test. And it is, in fact, worth 40 points. All right. First off, we're going to tell whether the points P represent a linear function, an exponential function, or neither. So we have to plot the points. So I have negative 2.25, negative 2.25, 1, 2, 1, 2, negative 1.5, negative 1.5, 0, 1. You notice that the intervals here are 2, 4. So I have 1, 2, 3, 4. And then I have 2, 4, 1, 2. So what does this look like? Well, that definitely looks exponential. All right, let's check out this next one. Negative 4, 7, negative 4, 4, 5, 6, 7, 8. So these are going by twos. I got 2, 4, 6, 8. So I have negative 4, 4, 5, 6, 7. I've got positive 1, 2. I've got negative 3, 6. I've got negative 2, 5. I've got 0, 3. Well, shoot. If I pull out my ruler, that is definitely a linear function. All right, there's quick 2 points right there. All right, make a table of values for the function, plot the ordered pairs on the graph, graph the function by drawing a smooth curve through the points, describe the domain and range. So I've got this function right here, which I'm going to put into Desmos calculator. So there we go. I've got 4 times 0.5 to the exponent value. So I'm going to plug in a negative 2. Oops. I need that to go back up there. Negative 2. 16. And then I put negative 1. And I get 8. So I'm not sure if you're seeing the answer over here. Here's the answer. 8. So if I go up here and I put in 0, I get 4. I put in 1, I get 2. Put in 2, I get 1. So now I plot all those points on here. So I have negative 2, 16. So negative 2, 16. Negative 1, 8. Negative 1, 8. 0, 4. 1, 2. Did you see how this goes by ones? 1, 2, 3, 4. And this one goes by twos. 2, 4, 6, 8. So that's why this is 1, 2. And then 2, 1. There's my exponential function. And what's my domain? Well, my domain is all of my x values. It goes on forever this way, and going high enough, it would go forever this way. So it's all real numbers. And my range, which is my y values, it'll go up forever. It'll come down, and it's going to stop at this line, which is 0. So y is greater than 0. All right, so pause the video if you need to make your corrections. Number 4, here's my exponential equation. So I'm going to plug these into here. So let's get into this. I have negative 4 times 2. And then my first one is negative 2. Negative 2 gives me a negative 1. And then I have a negative 1. Gives me a negative 2. And I have a 0, which gives me a negative 4. And then I have a 1, which gives me -8. And then I have a 2, which gives me -16. Is it okay to use the scientific calculator for these? Of course. It's what we've been using for our homework. So now I plot these, -2, -1. So I have -2, let me see, these go up by 2, 2, 4. So -2, -1, -1, -2, 0, -4, 1, 8, and 2, 16. So there's my exponential decay right there. And let's see what's my domain and range. Domain, which is my x values, it goes infinite this way, and if I went high enough, this would go infinitely this way. So I have all real numbers. And then my range, which is my y values, let me see, it goes down here, so it goes negative forever, but it stops. So y is less than 0. Stops at 0. Alright, pause the video if you need to. And don't. Hope you appreciate how we went from number 4 to number 7, just like that. For questions 7 and 8, use the growth for decay equations, which I give you the equations right here. Y equals a times 1 plus r to the t value, and y equals a times 1 minus r to the t value. Write a function that represents the balance after 2 years. You deposit $1,000. So my initial investment is $1,000. A savings account that earns 5%. So my rate is 5%. But I can't put a percent into a math problem, so I have to turn it into a decimal. Percents to decimals, I divide by 100. So you get 0.05. So let's plug these in. Y equals a, which is 1,000, times 1 plus 0.05 to t value. So 1,000 times 1.05 to the t value. What's the balance after 2 years? Oops, that's 1,000, not 100. The balance after 2 years would be 1,000 times 1.05 to the 2. So we'll go over here and we'll do 1,000 times 1.05, and we want to know after 2 years. After 2 years, the balance is 1,102.50. So $1,102.50. Okay. There's my equations. All right. You buy a used car for $4,599. Its value decreases by 11% every year. So my initial value is $4,599, and my rate is 11. My decay is 11, which is 0.11. So y equals 4,599 times 1 minus 0.11 to the t value. 4,599 times 0.89 to the t. What's the value of the car after 3.5 years? So it would be 4,599 times 89/100ths to the 3.5. So Let's put that into our scientific calculator. We got 4599 times 0.89 to the 3.5. 3.5. Don't let decimals throw you off. And what I get is 3058.64. Now the decimals keep going, right? It's 640486, but this is money. And money doesn't go beyond pennies, so $3,058.64 after 3.5 years. So how do I check it for 15 years? Well, I go into that equation right there, and I just put 15, and then I get the answer at the far side of this, which is $800.78. So I did the same equation, but I just put 15 for my exponent, and I get $800.78. All right, make sure you put those in. Stop and correct your paper if you have any corrections. Determine whether the table represents exponential growth, exponential decay, or neither. So 2 to 8, that would be times 4. 8 to 24, that would be times 3. Oh, that'd be times 5.3. Yeah, there's no consistency there. That is neither. Okay, let's hope the number 10 is a little bit better and more fun. 40 to 20, well, that's times 1/2, right? That's just half of it. Oh, look, that's just 1/2 of that. That's 1/2. Now, what's another way I could do it? I could put in my calculator 20 divided by 40, and I would get 0.5, which is 1/2. So I see this, it's multiplied by something between 0 and 1. So this, my friends, is exponential decay. There it is. Decide whether this sequence is arithmetic, geometric, or neither. 2 to 4, that's plus 2, plus 2, plus 2. So I just add 2 each time. Don't forget, if I add or subtract on a consistent basis, then it's going to be arithmetic function sequence. Okay, 64 to 32, that's times 1/2. 32 to 16, that's times 1/2. Times 1/2, look at that. Times 1/2, times 1/2, times 1/2. So that would be a geometric sequence. Okay, pause the video if you need to. Move on to the last page. So number 13, evaluate the function. So I'm going to go y equals 2, and then x equals 5, so I have to plug the 5 up there. That's 1, 2, 3, 4, 5. So 2 times 2 is 4, 8, 16, 32. So I have 32. Alright, y equals 3, 4 to the negative 1. So y equals 3 times 4 to the negative 1. So I do 4 to the negative 1, so 3 times 1/4, right? Because 4 to the negative 1 power is 1/4. So I get 3/4, which if you did in a calculator, we get 0.75. Okay. Y equals 1/2 to 5 to the third power. So 1/2 times 5 to the third power. So 5 to the third power, 25, 125, and then I divide 125 in half. So 125 divided by 2. 6. I get 2. And I get a 0. 1, 2 goes in that 5 times. So I get 62.5. And then y equals 0.5 to the x power, which is negative 4. So y equals 0.5 to negative 4th. So what that is 1 over 0.5 to the 4th. So 5 to the 4th power, 25, 125, 625. Let me just make sure that it's 625. 5 times 5. So there goes 2, 3, 4. Yep, to the 4th power. So I have 1 over 0.5 times 625. 625 times 0.5. Ay. Let me put this one into the calculator. Shucks. So let's see, 0.5 to the negative 4. I get 16. Mr. Blue's going to have to go back to the drawing board on that one. So I'll try and figure that one out. Oh, 1/2 to the 4th power. But why is it? I got it. Check this out. Okay. 0.5 to that power. So 0.5 to the negative 4th. 0.5 is 1/2 to the negative 4th. Oh gosh. 0.5 to negative 4th. So to get rid of this negative, I have to flip this. So it's 2 over 1 to the 4th. So it's 2 to the 4th power, which is 2 times 2 times 2 times 2. 4, 8, 16. Ding, 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 ding. Sorry about that. Okay. Last one. The coronavirus often causes illnesses among people who sneeze on each other. Suppose that a single COVID bacteria virus in a batch of coughs begins doubling every minute. Complete the table below to represent the number of viruses after X minutes. Assume that none of them die. So it doubles every time. So it's times 2, times 2. So 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64. There's my chart. Write an equation in the form of y equals a times bx. That can be used to calculate the number of bacteria in the food after the number of items. So a is our initial one. So here's 1. So y equals 1 times our rate of change, which is 2, to the x value. So that's actually our equation right there. And so if we want to, how many bacteria will there be after 20 minutes? It'd be nice if you guys guessed, because it's pretty cool how crazy this number gets. There it is at 6, but at 20, y equals 1 times 2 to the 20th. So we have 1. So 2 to the 20th. I'm not going to do that. That's too many. It's too many. So let's go 2 to the 20th. 1048576. And what's 1 times anything? Well, that's what it is. So 1048576 576, 1, 2, 3, 1, 2, 3. You have, in 20 minutes, you started with 1, and in 20 minutes, you now have 1,048,576 bacteria or viruses. It's crazy. Alright, pause the video where you need to make your corrections, and I hope you did well.